Dear students, today we are going to see another important theorem. The theorem is fundamental theorem of algebra. Okay, now what is the statement of the theorem? We'll see. Suppose P of z is equal to a naught plus a1z plus a2z square plus and so on a n z power n, where the coefficient, the z power n coefficient a n is not equal to 0 and aj is nothing belongs to c. So these are the coefficients which are there. Okay, is a polynomial of degree n, which is the positive one, that is nothing but greater than 0. Then there is a 0 for p of z, means it has a root. 0 means a root z naught, such that there exists a z naught belongs to c, such that p of z is nothing but equal to 0, means z naught is nothing but 0 of this polynomial. Now what is this given? So how we are going to prove? We'll take that in a contradiction manner. We'll suppose that if p of z is not equal to 0, okay, we'll take that the theorem is nothing but fail, and we suppose that p of z is not equal to 0. Then we'll try to prove the theorem. We'll get a contradiction in the end, so that we can prove that p of z is nothing but equal to 0. So we'll go in a contradiction manner. So first we'll take this one in the form of like this. So proof. We prove this theorem by contradiction. Okay, by contradiction. Theorem by contradiction. Okay. So what we'll do is, suppose if possible that the theorem is false. We are just going in a contradiction manner. The theorem is false. That is, p of z naught is not equal to 0 for all z naught belongs to c. Okay, so p of z naught is not equal to 0 for all z naught belongs to c. Now this is nothing but we are taking a contradiction manner. So let us take f of z is equal to 1 by p of z. I am considering a function capital F of z which is equal to 1 by p of z. Then the f of z is entire function, means it is analytic in the region. Okay, now we prove that f of z is also bounded function. It is nothing but entire function, and we prove that it is a bounded function. So when you are able to prove it is a bounded function, then it may leads to the contradiction manner, means it may leads to some constant like that we'll get. Okay, so f of z is also a bounded function. So we'll consider p of z. Now p of z is nothing but equal to a naught some a1z some a2z square plus and so on plus a n z power n. Now this p of z I have taken in the form of like this, same as usual what we have chosen, right? Then next, so we'll take z common here, means z power n common, the degree. So the z power n is nothing but common. So I'll write first term this is an. Okay, an into z power n. Okay, plus before term the before term is an minus 1. Here z power n minus 1 will be there. So here z power n. So you'll get z power minus 1. You'll get z power minus 1 here actually. If you multiply, then that will be in the denominator. Plus an minus 2 means z square plus and so on. So here an minus 1, an minus 2 like that. So I am writing in a from the last to the first. So plus and so on. Here this is a naught. So a naught by z power n. This is the last term which I am writing. A naught by z power n. If you multiply this one, you will get again a naught. Okay, so what I will do is, I may take this is p of z as it is like this. This I will write a n z power n. This is z power n into a n plus this I will write as w. I will write as w. Okay, where w is equal to a n minus 1 by z plus a n minus 2 by z square plus and so on plus a naught by z power n. Now this everything I have taken means this whole thing I have taken as w. Okay, so that I have written as p of z is equal to z power n a n plus w. Okay, so then after this we will try to take in the form of like this. After writing that, we will try to write that f of z is equal to 1 by p of z. So what we have here is p of z is equal to z power n into a n plus w. Now this is what we have. Okay, so what is that now? Now capital F of z is equal to 1 by p of z. So 1 by z power n a n plus w. Now this is what we have. So I may take in the form of like this. So I'll just take in the form of like this. I'll try to find out w value. So limit z tends to infinity, w is equal to 0 means this entire thing for this, if z tends to infinity, this will be equal to 0. So 1 by z tends to 0. So w is equal to 0. So therefore for epsilon is equal to mod a n by 2 greater than 0, there exists r greater than 0 such that r greater than 0. For epsilon equal to mod a n by 2 greater than, there exists r greater than 0 such that w minus naught. This is the definition of this. I am writing the definition. W minus 0 which is less than some epsilon by 2 means epsilon is nothing but a n by 2. For mod z which is greater than 0. Okay, then so therefore what we can write here is for mod z which is nothing but greater than 0. So this I may write as mod w is less than mod n by 2 for all z with mod z greater than r. Now we will try to find out the value of a n plus w. A n plus w we will try to find out. So that implies we will try to find out a n plus w mod which is greater than mod a n, okay, minus mod w, right, which is greater than mod a n minus mod w which is greater than mod a n minus mod w. Mod w is what? Mod w is nothing but less than mod a by 2. So what I will write is here is greater than, this is mod a n by 2. So this is what you will be getting as, that is nothing but equal to mod a n by 2. So you got as mod a n plus w is you got as mod a n by 2. Okay, so this is greater than equal to, I am just writing z1 plus z2 form. Mod z1 plus z2 is nothing greater than equal to mod under the mod z1 minus mod z2 under mod, which is greater than equal to mod a n means mod z1 minus mod z2. Z2 is nothing but the value is mod a n by 2, which is nothing but mod w is less than mod a n by 2. So you will be getting as that value. Okay, then so therefore what we got is mod a n plus w is greater than mod a n by 2 for mod z greater than r. Okay, mod z greater than r. So let us take this as number 1 and this as number 2. Okay, so therefore what we can write here is For mod z greater than r, we'll try to find out the value. So for mod z greater than r, now we'll try to find the value of the thing. Mod z greater than r, I may write as mod f of z, mod f of z, mod f of z is equal to 1 by z power n a n plus w, the mod, total mod. I have taken the mod. Okay, now this is nothing but, this is mod z power n mod a n plus w. I have taken the mod a n plus w. Now this is 1 by mod z power n, means mod n is nothing but greater than n now. So I may write this as some r power n, and mod a n plus w. Mod a n plus w is nothing but mod a n by 2. So I may write as mod a n by 2. So that is equal to 2 by r power n into mod a n. Now I got as, this 2 will go to the numerator, 2 by r power n mod a n. Now this is how we got the calculation. So therefore this is less than, if I apply this is less than or equal to 2 by this one. Okay, so therefore conclusion, we write like this in the form of like this. So therefore mod f of z is less than 2 by r power n into mod a n. This is what we got. Okay, so this is the circle. Okay, the circle is nothing but center 0. This is r. This is nothing but CR. Okay, so therefore f of z is, this is what is given, is entire. F of z is entire, and that implies f of z is entire means f of z is continuous. It is continuous inside and on R or CR. Okay, continuous inside and CR. So therefore that implies there exists m greater than 0, such that mod f of z, which is less than or equal to m inside, okay, inside on CR. So on CR, inside on CR. So consider, I'll just consider the value of k. I may write as k is equal to maximum of the value m and the value which we got, that is 2 by r power n mod a n. I got this one. This is the maximum value which you are going to take for the f of z. So therefore what is that now? What we need to prove? We need to prove that it is nothing but bounded. So therefore it is bounded by the value of these two, that is m and 2 by r power n mod n. Whatever the maximum value is there, that we are going to take such that it becomes as a bounded. So therefore what I got, capital F of z is bounded entire function. Okay, we got as bounded entire function, and hence it is a bounded entire function, and hence a constant function. Why it is constant function? According to the Livy-Wallace theorem. Constant function by Livy-Wallace theorem. Livy-Wallace theorem. According to that, every bounded function leads to a constant function. Now this is what we got. So therefore what I can say, capital F of z is equal to 1 by P of z. So that implies I may write that P of z is a constant function. So it is a constant function. What I got is a constant function I got. So this is a contradiction, because it is not a constant function, it is a polynomial which is given. Now what we have chosen that P of z is not equal to 0 is wrong, because we got as P of z as a constant function. But what is that now? This is a contradiction. As P of z is a constant polynomial. I may write as it is a polynomial. It's a polynomial which I got. So therefore there exists Z0 belongs to C such that P of Z0 is equal to 0. Therefore P of Z0 is equal to 0. So what we got is, we have proved that f of z is a bounded entire function, but every bounded entire function leads to a constant function, such that by the Liveless theorem it is nothing but a constant function. So P of z is a constant function we got, so that is a contradiction. So P of z is not a constant function, it is nothing but a polynomial. So therefore there exists Z0 which belongs to C such that P of Z0 is equal to 0. So this is the way to do the fundamental theorem of algebra. Now next we will go for the another important point regarding this polynomial. So that P of z will take a polynomial, but how you got that polynomial, that we'll try to find out in this manner. Okay, suppose P of z is nothing but equal to, suppose that P of z is nothing but equal to a0 plus a1z a2z square plus and so on an z power n. Now this is what we have, the P of z, a polynomial of degree n, then we can write this P of z as, P of z is equal to, we write as an z minus z1 z minus z2 and so on z minus zn. These are the factors. This is a leading coefficient actually, and these are the nothing but the factors which we have for the coefficient. For some zi belongs to C. Now how we got that solution? So there exists a z belongs to C such that P of z1 is nothing but equal to C. I will write z1 is equal to C. Such that P of z1 is equal to, just now we found that P of z0 is nothing but equal to 0. So z0 is nothing but a root. So here z1 is the root of this one. Then how you write this one? So I will write that P of z is equal to, I will write as P1 of z into z minus z1. Now by writing in the form of z minus z1, and P1 of z is nothing but a polynomial. P1 of z is a polynomial of degree, P1 of z is nothing but of degree n minus 1. Okay, so one thing I wanted to make it clear this. Suppose for example, I may write this as some x cube minus 3x square plus 3x plus 1. This is what we have. This is a cubic equation, that is a cube minus 3a square b plus 3ab square plus b cube. A cube minus 3a square b plus 3ab square minus b cube. Generally x is equal to 1 is a solution for this. If you put x is equal to 1, you will be getting as 0, means 1 minus 3 and the plus 3 minus 1, these two gets cancelled, you will get 0. So what I can write is x minus 1 is a factor. Now if I divide this x minus 1 to this, you will get a polynomial here. You will get a polynomial. X minus 1, even though it is nothing but a root, you will get another polynomial whose degree is less than this. The degree is 3, here degree is 2. You will get a quadratic equation here. You will be getting quadratic equation. This quadratic equation is nothing but P1 of z. Now there is a quadratic equation. And z minus z1 is nothing but a root, means 1 is the root for that. So this is how we get like this. So similarly, if I suppose that there is another root for the polynomial which is having, so there may exist one more root. The root, this is how they will be common. So z minus z1, and there exists a z minus z2, and you may get a polynomial p2 of z. You will get a polynomial p2 of z. Okay, I may write this as like p2 of z here I write. Now you will be getting as z minus z1 and z minus z2 p2 of z. So degree of p2 of z may leads to n minus 2. You will get further less degree. Okay, further you are going to have like this, you may have z minus z1 and z minus z2 and so on z minus zn, but you will be having one constant coefficient will be there, that I am writing here as an, where an is a leading coefficient. We may say that an is a leading coefficient. Now this is how the polynomial, the roots will be there. This is how we are going to have, that is an, z minus z1, z minus and so on, z minus Zn, you will be getting as some an as a coefficient. Means this polynomial may decreases to up to the level where you will get a coefficient. Now this is how we can write that fundamental theorem of algebra in the form of like this. So this is one of the important point. Now we will try to prove another important theorem. The theorem is mean value theorem. Okay, Cauchy's mean value theorem. Okay, another important theorem, Gauss mean value theorem. Okay, now I'll just write this. Suppose mod f of z is less than or equal to mod f of z naught, and f of z is analytic. F of z is analytic in some neighborhood. In some neighborhood, mod z minus z naught less than epsilon, then f of z is constant. F of z is constant throughout the neighborhood z minus z naught, which is less than some epsilon, and f of z is equal to f of z naught for all z belongs to some c. Okay, this is how we got. This is how. First we will prove the Gauss mean value theorem, then we'll try to prove this inequality, and based on this inequality we'll have one more theorem. Okay, so first we'll try to prove that. Now we'll take a circle in the form of like this. This is a circle. Okay, now this is the point, and this is, I will take C rho. Okay, C rho, and this is the point Z naught, and there exists one more point here, Z1. Now this is what we have, and I may take Z over here. This is another point, Z is there in the outside of the region. Now this is nothing but some rho. Z1 minus Z naught, or Z1 minus Z naught is nothing but rho, and C rho is the circle. And this is the circle C. Let us suppose this is circle C outside. Okay. So what is that now? We will consider the circle now. I am taking a circle C rho such that Z1 minus, or I may write as Z minus Z naught. Z minus Z naught is equal to rho, or I may take Z minus Z1 equal to rho. I may just considering the point Z here such that Z minus Z1 is nothing but equal to rho. If I am taking the point, this Z naught I am taking as Z. Now I am putting, if I Z the value lies here, means Z here it is lying here. So I may write that Z minus Z1. Or if I suppose I want to take another point, I may take Z2, Z3 like that. So Z is nothing but a common thing, that where you can replace any of the point. Z1 is nothing but lying the point over here like this. Okay. So this point, maybe this point you can write here Z naught minus Z1 also you can write here, like that you have. So Z minus Z naught. So therefore, and Z of theta is equal to, now I am writing the equation. Z of theta means I will write like this. Z is equal to, Z of theta is equal to mod Z minus Z1 is nothing but equal to rho. Okay, mod Z minus Z1 equal to rho. So what I am writing here is, I will take now here as Z naught. So instead of writing Z1, let us take Z naught. Z minus Z naught is equal to rho. So this implies, so Z is equal to Z naught plus rho e power I theta. Rho e power I theta, where theta belongs to 0 to 2 pi. 0 to 2 pi. Now what I supposed here? Now Z minus Z naught I supposed, means Z here and Z naught here. This is Z1, anything else. Okay, not to be confused, because Z minus Z naught, I am taking Z over here, Z naught here. Here Z1 is that point. Anything you can take. Okay, now we got Z is equal to Z naught plus rho e power I theta. Okay, this is how we got. Now let us take Z dash of t. Z dash of theta is equal to, Z dash of theta you will be getting as, Z dash of theta is equal to rho I e power I theta, where theta is nothing but belongs to 0 comma 2 pi. Okay, this is how we got. So this is what we have, rho e pi e power I theta. Since f of z is nothing but analytic, f of z is analytic inside and on C. Inside and on C. C means here I'll take C rho. C rho. So by Cauchy's integral formula, we get. Now I'll write that one. F of z naught is equal to 1 by 2 pi I integral 0 f of z by z minus z naught dz. This is according to Cauchy's integral formula. So therefore I'll write as f of z naught is equal to 1 by 2 pi I integral 0 to 2 pi. I'll write 0 to 2 pi f of z. Z is nothing but z naught plus rho e power I theta. So I will write z naught plus rho e power I theta by z minus z naught. So z minus z naught is rho e power I theta. This is rho e power I theta into I d theta. Okay, this is dz. If at all you want to find out dz from here, so dz is equal to what you will get, rho I e power I theta d theta. That's the value of dz. So I rho e power I theta gets cancelled. Okay, then you will be getting as this I also will gets cancelled. Now what you got here is simply you got in the form of like this. So you got like this. So what is you got now? F of z is equal to f of z naught is equal to 1 by 2 pi integral 0 to 2 pi f of z naught rho e power I theta d theta. You got this I and this I gets cancelled. Now this is what? This is called Gauss mean value theorem. This is the result of Gauss mean value theorem. This is called Gauss mean value theorem. This is what Gauss mean value theorem. Okay, this is what we got as Gauss mean value theorem. Now we will go for the actual theorem. This is Gauss mean value theorem. We have to find out first this one, then we will go for the theorem. Now we go for the theorem. Now we have by the hypothesis we have in the formula like this, mod f of z is less than or equal to mod z naught. Now this is what it is given in the hypothesis, f of z less than or equal to f of z naught. Okay, so what is f of z here? So that I may write this as f of z as mod f of z naught plus rho e power I theta, which is less than or equal to mod f of z naught. Now this is what it is given in particular for all z. Since z naught we know that z naught rho e power I theta. Okay, this is what we have. Okay, so what we'll do is we'll take this one. We'll take this value we'll take. So therefore we'll take this one. This is f of z naught is equal to 1 by 2 pi integral 0 to 2 pi f of z naught plus rho e power I theta d theta. We'll take mod on both sides. Like this if you take mod. Okay, so what you'll get is mod f of z naught is less than or equal to 1 by 2 pi integral 0 to 2 pi mod f of z naught plus rho e power I theta mod d theta. You got in the form of like this. Means f of z naught is less than or equal to 1 by 2 pi integral 0 to 2 pi f of z naught plus rho e power I theta d theta. This you take it as number 1 will take. This is as number 1. Okay, this is number 1 which we have taken. So what we'll do now? So this from here, from star you take from star. So from star. Okay, this is from this. This is from this. Now this is from star. Now what is the f of z naught is greater than or equal to this. So mod f of z naught is greater than or equal to mod f of z naught plus rho e power I theta you got. Now this is what we have here. So what will supposed to prove that theta is nothing but belongs to 0 to 2 pi. Theta is belongs to 0 to 2 pi. Now we'll consider in the form of like this. Integral 0 to 2 pi is nothing. Integral 0 to 2 pi mod f of z naught dt is equal to, you will be getting as 2 pi into mod f of z naught. This is the thing which we can have. This is integral 0 to 2 pi f of z dt is equal to 2 pi into mod f of z naught. So this term can be taken as 2 pi into f of z naught. So what we'll do here is we'll try to take the term which is this. I may take this one to this side. So from here what I'll do is I'll take in the form of like this. I'll be taking in the form of like this. Now this one from here, this term I may write as integral 0 to 2 pi mod f of z naught minus mod f of z naught plus rho e power I theta d theta is greater than or equal to 0. Okay, so what is going to happen here? This integral is 0 to 2 pi. I have taken, actually I have to take integral 0 to 2 pi. Integral 0 to 2 pi. See from here, integral 0 to 2 pi, integral 0 to 2 pi. So if I take integral 0 to pi, you will get 2 pi. This also you will get 2 pi. So 2 pi gets cancelled. Again you get same thing. So this I am changing in the form of like this. So what I got is integral 0 to 2 pi f of z minus this one is greater than or equal to 0. This will suppose we'll take it in the form of number 2. This is number 2 which we got. So what is by 1? What is that now? This one. We'll suppose this. Okay, that will take. We'll try to take that. Okay, this one. So from here what we can take here? I'll take this one to this, but I'll include this one. This I'll take in the form of 2 pi. Means I'll take like this. Integral 0 to 2 pi f of z naught dt is nothing but 2 pi. I'll take 2 pi here. If I take 2 pi, okay, I'll write like this so that you'll understand clearly. From 1, what I'll take 2 pi here I'll take. So this is 2 pi mod f of z naught, which is less than or equal to integral 0 to 2 pi f of z naught plus rho e power I theta mod d theta. So what I have supposed? I suppose this 2 pi to this side. This is denominator, so I have taken to this side. So this came written as integral 0 to 2 pi mod f of z naught d theta, which is less than or equal to integral 0 to 2 pi f of z naught rho e power I theta mod d theta. Like this we have taken. Okay, this is what we have taken, right? So therefore what is that now? This one, if I take to the left side, 0 to 2 pi mod f of z naught minus f of z naught f of z naught plus rho e power I theta mod d theta is less than or equal to 0. This term is again we got as less than or equal to 0. This is, let us suppose this is number 3. Now one term what we got? This term is less than 0 and this term is greater than 0. So less than 0 and greater than 0. I may write as it is equal to 0. So what I can write here from 1 and from 3 and 2 and 3. So from 2 and 3 we get that integral 0 to 2 pi mod f of z naught minus mod f of z naught plus rho e power I theta and d theta is nothing but equal to 0, because a less than equal to b less than equal to a, I may write a equal to b. In the same manner, it is less than equal to 0, the one is greater than equal to 0. So both if you equate, that you will get as equal to 0. So therefore what you got here is f of mod f of z naught is equal to f of z naught plus rho e power I theta mod I theta is equal to 0. This integral will go that side, that becomes 0 again. Okay, so therefore you will be getting as, that implies you will be getting as f of z naught is equal to mod f of z naught plus rho e power I theta. Okay, but z naught rho e power I theta is z. So I may write that mod f of z naught is nothing but equal to f of z, mod f of z we got. For all z belongs to, for all z, for all z which we have. Okay, where z minus z naught is, where z minus z naught which is less than some epsilon. You can take less than epsilon or you can take any other inequality. Okay, so therefore what we got here is this. So therefore the conclusion, I may write this one, I'll write this for all z. Okay, so this is what we got. So what we can say here, as z1 belongs to 0. Now I am taking as z1 belongs to the 0, the circle, on the circle. I may write we have f of z1 which is nothing but belongs to f of some z0, mod f of z1 is nothing but equal to f of z0. Now what are the value you take here z? The z may be z1, z2 and so on. So it may be equal to some constant, that is nothing but z0. What are the value of z0? You can take that. So therefore I can conclude that f of z is nothing but equal to mod f of z0. This is what we can conclude for all z in mod z minus z0 which is less than some epsilon, whatever it is. Means this is the C row actually which we have taken. This is the point z0, this is the point z1, there is a point something z. Now we proved that this z may be, you can take any other value, any value you can take, that may be equal to one constant value f of z. Like z1 you may write here, z2 you may write here, whatever the distance between any two, the center and the point on the circle. So what you got, f of z is nothing but equal to f of z0 for all z. So therefore what is that now? I can write that f of z is nothing but analytic, f of z is analytic on mod z minus z0 which is less than some epsilon, where z1 is nothing but arbitrary. This is, I can take z1 is an arbitrary, you can take it is an arbitrary value. Okay, so therefore and mod f of z is nothing but a constant. So this is a constant value. See, whatever the value you take, it is nothing but a constant. You are getting only one value, that is f of z0. So therefore what we can say, therefore f of z is nothing but constant, which we got as a constant. So what the proof wanted to we have is f of z is nothing but constant. So to prove this, we need to prove first Gauss mean value theorem. Then by using the Gauss mean value theorem, we will try to prove this theorem. Now this is how we have done the theorem. Now we go for the max by using this Gauss, by using this concept, that is mod z is equal to mod f of z is equal to mod f of z0. We have another important theorem called maximum modulus theorem. So that is very, very important. That is maximum modulus theorem. Now we'll write that statement. Maximum modulus, another important principle. I can write that principle or theorem. Maximum modulus principle, minimum modulus principle is there. But we'll write first maximum modulus principle. Suppose f of z is a non-constant, f of z is non-constant analytic function, on a domain D, then mod f of z never assumes its maximum value on D. Never assumes its maximum value on D. That is there exists no point z0 belongs to C such that mod f of z is less than or equal to mod f of z naught, or max of z belongs to D mod f of z is not equal to max of for all z naught belongs to D mod f of z naught. Okay, this is how the theorem statement says. Now what the theorem says now, that if you understand what the theorem says, then it is very easy. See, suppose f of z is a non-constant analytic function. It should not be a constant it should not be a constant function. F of z should be analytic. Then f of z never assumes its maximum value. Let us suppose you take a circle. Now this is a circle which we have. Okay, circle C. Now I wanted to take a function f of z such that f of z is nothing but analytic and non-constant. Okay, right. F of z is nothing but I have chosen that f of z is nothing but analytic. Now this f of z should have a value which is nothing but maximum, such that it should not be in this condition. Means f of z nothing but less than or equal to f of z naught. Should not be less than or equal to f of z naught. So what that meaning is, it should never be a maximum value on D. Okay, it should not have a maximum value on D. Suppose for example, what is saying that then f of z never assumes its maximum value on D. Now this is, let us suppose D there is a circle. Okay, it should not have a maximum value on D, means there should be no other value in this C such that it is maximum. Okay, it is maximum. Now where that maximum value should exist? Even though if it is having a maximum value, it should exist on the boundary only. Means the maximum value should be on the boundary itself only. No other value except the point which is on the boundary. No other value should be there inside such that it is a maximum of f of z. Means it should bounded by such a value, that value should be on the boundary only, and it should never assumes a maximum value inside the region C. Okay, suppose for example, this is what the same the theorem says clearly that f of z will assume its maximum value on the boundary, otherwise it doesn't have any value which is maximum inside D. It should not have any inside the region in C. Should not have any maximum value. It should be, if it has a maximum value, it should be on the boundary only, not in the inside the D. So that is what he wanted to convey us. So we will try to prove that in the form of like this. We'll go further in a contradiction way. Suppose we will say that there is a maximum value inside the C. Then what is going to happen, that we'll see. So we'll try to prove in a contradiction manner. So the proof is by contradiction. The proof is by contradiction process. The contradiction. Okay, we'll try. Suppose there is a point z naught. Now I'll take a z naught which is belongs to Z such that I am taking the point z naught which is belongs to such that I may take f of z which is less than or equal to f of z naught. Now this is what I am taking, means I am taking a point f of z naught which is greater than f of z. Means this is the value which is I am taking that. Otherwise f of z is less than or equal to f of z naught. Whichever the point is there, z naught is nothing but is greater than this one. Okay, this is what for all z belongs to D. Okay, now since f of z is a non-constant analytic function, is a non-constant analytic function on D. It's a non-constant analytic function on D. So therefore I'll take a D. This is D. Okay, there are some points here. I'll take z naught, or I'll take z naught, and somewhere z1, somewhere z2, and so on. I may take zn. These are the functions, and you can understand that it is nothing but D is nothing but a open connected set. D is an open connected set, and whenever it is open connected, there exists a polygonal arc. Now I may write as polygonal arc like this, so some other point like this. Now these are the polygonal arcs. Okay, these are the polygonal arc. Okay, now there exists a distance D. I may take this as distance D. which is the shortest distance. D is the shortest distance between them. So I may take a circle which is nothing but under the D, which is neighborhood. I may take another circle which is having Z0 and Z1. I may take another circle which is having Z1 and Z2. I may take another circle which is having Z2 and Z3. I may take another circle which is having Zn minus 1 and Zn minus 2 and Zn minus 1. I will take another circle Zn and Zn minus 1. Okay, this is nothing but N0 and this is nothing but N1. Okay, and this is nothing but N2 and this is N3 and so on. This is Nn. Now I have taken all the circles, means all the neighborhood which is being covered Z0 and Z1. Now Z0 is nothing but only the Z0 is there, but Z1 is nothing but it is having the point Z1 as a center and Z0 will be there inside the point. Like that, Z1, Z2 will be the center for that one. Mean all Z1, Z2 will be in Z2 and Z2 and Z3 will be in the N3. Like that, these are the neighborhoods. Now these are the polygonal arcs which is there in that. And D is the distance between, the smallest distance is there. Now if suppose I have considered like this, then what are the things which you are going to have? Okay, so I'll write what we have considered. What we have considered in a theoretical manner. I'll write. Let Z belongs to D. Z belongs to D, and let D is equal to distance between Z1 and the Z0 and D. This is the distance D. These are the distance. What are the distance which we have taken? Okay, as D is open and connected. So it is open connected. There will be there exists a polygonal arc. There exists a polygonal arc. Polygonal arc L. This is the polygonal arc L. All. Okay. Polygonal arc L, which is joining the points. Polygonal arc joining Z0 to Zn, the last. Okay. If I take N here, capital N here, if I write Z, Z0 to Z, I can write like that. Okay. Z0 to Z, lying in D. Lying in D. Okay, and we'll choose Z0, Z1, Z2 up to Z n minus 1 on L, which lies in D. Okay, on L such that lies in D such that all the points, just now what we have taken, the same thing, all the points which we have. Okay, so therefore what is that now? The distance between 2 points should be always less than D. Okay, it is not more less than D. So I'll take that zk minus 1 is less than some D. The point which we choose, these two will be less than D. These two will be less than D, like that. Okay, so therefore, and the k is not what equal to 1, 2 and so on n. Okay, where I may choose this Zn may be equal to Z. I may write this as Zn equal to Z. I may choose Z is equal to some Zn, the last point Zn. Okay, this is what we have. And we'll write the neighborhood, that is nothing but Nk is equal to Nd some Ik, where k equal to some 0, 1, 2, so on n. D is nothing but distance. I, k, the distance between those two values. Ik. Okay. Now we have f of z is analytic on n0. Now we have taken a function f of z which is analytic on n0, and so therefore what that first one, z0 belongs to n0 and now according to the previous theorem what we have proved, what we can write here, z0 belongs to n0. So what we can write here, mod f of z is less than or equal to mod f of z0. This is for all z belongs to n0. This is the condition which we have taken, because the chosen point is nothing but greater than or equal to z. Now that is what we have chosen. So by previous theorem what we can write, If this is a condition, what is that? Now previous theorem we have taken that f of z is nothing but equal to some constant. So by previous theorem we get that f of z is nothing but equal to f of z naught for all z belongs to n naught. This is what we got from the previous theorem. We have taken this and we have proved that f of z is equal to f of z naught. So that we have taken now. So what we'll do now? So we note that f of z is analytic on, again now we have taken n1 we got that f of z is equal to f of z naught. Again what we'll choose? We'll choose n1. In n1 we'll take z1 and z naught. So f of z is nothing but equal to less than or equal to f of z1. F of z naught is less than or equal to f of z is less than or equal to f of z naught. So you will be getting as f of z is equal to f of z1. So therefore we will be getting that again constant. F of z1 is nothing but equal to f of z naught. That is also a constant. So n1 will choose, again n2 will choose, like that we'll choose up to the n. Okay, so what is that now? We'll take that, note that f of z is analytic. F of z is analytic on n1 for all n1 comma z1 belongs to n1 and z2 or z0 belongs to n1. z1 and z0 both will be there in that point. Okay, so therefore what we get? F of z is less than or equal to f of z1. F of z1 is the first point. Then f of z is nothing but less than or equal to some f of z0. Now we got as f of z is less than or equal to f of z0. This is for all z1 belongs to n1. This is for all z1 belongs to n1. Means z0 belongs to n1. What we got here is f of z is not equal to f of z1. F of z is less than or equal to f of z0. Now what we can write the conclusion? Therefore what we can write here? F of z is equal to f of z0. So what we'll write here? Z0 is nothing but this is equal. So therefore I can write f of z is nothing but equal to f of z1. F of z1 for all z belongs to n1. Whatever the value of z is there, it is nothing but belongs to some z1. So this is for n1 we got. Now next we'll take n2. Similarly we go for n2. n2 also contain 2 points, that is z1 and z2. Okay, similarly f of z is analytic in n2. So there z1 belongs to n2 and z2 belongs to n2. So therefore mod f of z is less than or equal to mod f of z1, where z1 is belongs to n2. Mod f of z is less than or equal to mod f of z2 comma z2 belongs to n2. Okay, so therefore what is that now? F of z1 is f of z2 is also belongs to f of z2, and this is also there. So what the conclusion now? We can write the conclusion is, so therefore what we can write is f of z is equal to f of z1 for all z belongs to n2, and this also belongs to f of z2, that also belongs to f of z2. Okay, z2. See, f of z belongs to f of z1. F of z1 is nothing but equal to f of z2. Then f of z2 is nothing but equal to f of z2. Therefore, f of z2 is equal to f of z2 for all z belongs to n2. Now you got the value. What are the value you are choosing? Means z1, z2. What are the value you are choosing? You are getting as one constant value f of z. So therefore, what we got the conclusion is, the last conclusion. If you go on like this, continue in the form of like this up to n. Up to n if you continue. So you will be getting as f of z is equal to some f of z0 you are getting for all z belongs to n minus 1, the previous term. But what is that last one? But zn belongs to nn. The last point, the point which we have taken is zn belongs to nn. But you are getting as f of z is nothing but equal to f of z0 for all n minus 1. So therefore I may write as f of z is equal to f of z naught, that may be equal to, I may write as, the last point is zn, no? So I may write as f of zn, that is may be equal to, if you take f of some z dash. So that implies I may write as f of z dash is equal to some f of z naught. So I may take it as that value as this. For all z dash belongs to D. Z dash is sum of the point. Okay. So therefore what we got? We got as f of z is nothing but a constant function we got. What we got as f of z is a constant function we got. So what are the point we are going to choose? All the points are leads to the one point itself, and there is nothing but f of z. So f of z we got as a constant function, but what is given in the statement? F of z is a non-constant function, but what we got? F of z is a constant function, which is a contradiction. So contradiction, which is a contradiction to the hypothesis, which is a contradiction to the hypothesis. Contradiction to the hypothesis. Okay, contradiction to the hypothesis. So therefore f of z is a non-constant function. It should be never be assumes its maximum value inside the, when whatever the value you have to choose the maximum value, it should be on the boundary. This is how we can complete this theorem, that is called as a maximum modulus theorem. Okay, there is another important small theorem that we'll try to find out very easily. Then based on that we'll have one more small problem that we'll do. Okay, this is about the maximum modulus theorem. Once again, what is the maximum modulus theorem? Maximum modulus theorem says that whatever the f of z is nothing but analytic in the region, it never assumes its maximum value inside the D. Means f of z is less than or equal to f of z naught. It never happens. If at all if wanted to have a maximum value, it should be on the boundary itself only. The same thing we have proved in the previous theorem. Now we'll prove a small thing that like this. The small problem. Suppose f of z is analytic at a point z naught, then all derivatives of f exist and are analytic at z point, at the point z naught. So proof. So all the derivatives, suppose that f of z is nothing but analytic at a point z naught, and all the derivatives also will be exist and analytic at that point. Derivatives also analytic at that point. That we are going to prove with the help of the Cauchy's integral formula for higher derivatives. Okay, so let us take this is the point z naught, which is less than some this is on C. Okay, this is the point where it is having. Okay, now this is some epsilon. Okay, less than this nothing but epsilon. Mod z minus z naught. This is z, and this one is nothing but less than some epsilon. Okay, total is nothing but epsilon. Okay, so f of z is analytic. F of z is analytic at z naught. So that implies there exists epsilon greater than 0 such that f is also analytic. F is also analytic on mod z minus z naught is less than epsilon. This is nothing but f of z is also analytic in this region. Okay, and on C. Okay, so therefore what I'll write is f of double dash of z, f double dash of z is equal to 2 factorial by 2 pi I integral C f of s minus z whole cube ds. Now this is from the Cauchy's higher order derivative. You know, f power n of z naught is equal to n factorial by 2 pi I integral C f of z minus z naught whole power n plus 1 dz. Now this is what the Cauchy's integral for higher order derivative. The same thing we have taken, but here n means twice. We have taken 2 derivative 2. So we can say that this is f dash of this shows that f dash of z is analytic at z naught. Now this is the value such that we can say that f dash of z is analytic. So repeating the result for result for result for result to f dash of z, we can prove f double dash also. We can prove this one for the f, this is for f dash. We can prove for that to see that f double dash of z is also analytic at z naught. This is also analytic at z naught. So therefore we can say that f power n of z is analytic. So this is also analytic at z naught. No, means the derivative also is analytic at z naught, because since it is satisfied here, so we can say that f dash of z is analytic. Then we can prove that f double dash also will be analytic. Means you will be getting twice you will get 3. In the place of 3 here you will be getting as 4, like that. Okay. So therefore, and so on, if we can prove f power n of z is also analytic at z naught. So based on this, then we have one more small theorem that is called as a moreras theorem. This topic will be completed. So moreras theorem, by using this small problem, we'll try to prove that. Moreras theorem is nothing but a converse of a Cauchy-Gauss theorem. So moreras theorem, moreras theorem. Statement, what the statement says: suppose f is continuous on a domain D, let integral c f of z dz equal to 0 for every closed contour C contained in D. For every closed contour C, it is nothing but contained in D. Then we prove that f is analytic. F is analytic in D. It's a converse statement of Cauchy-Gauss theorem. What the Cauchy-Gauss theorem says that if f is analytic in the closed contour C, then we should prove that integral C f of z dz equal to 0. But here, if integral over C f of z is equal to 0, then f is nothing but analytic. That we need to prove. So by using the above problem, we'll try to prove this. It's very simple. So under the hypothesis, what is given? F of z has an antiderivative, because it is continuous on D. F of z has an antiderivative, say f of z, capital F of z. That is capital F of z is nothing but equal to small f of z for all z belongs to D. Okay, it has an antiderivative. Cauchy-Gauss theorem also we have. By using antiderivative we have proved. By using the Green's theorem, by using the antiderivative, these all conditions which we have used for to prove Cauchy. So therefore it has a antiderivative f dash. So therefore what we can say, f is analytic on D, because f of z is analytic, so f is also analytic. Then f dash is also analytic. How we have proved that f dash is analytic on D? Just previous problem. In the previous problem we have proved that f dash is also analytic on D, and f double dash is also analytic on D, and f power n is also analytic on D. That we have proved. The same thing we have applied by the previous result. So f dash is nothing but analytic. Then what we can say, if f is analytic and f dash is analytic, then f of z is also analytic. So f of z is also analytic in D. Now this is how we can prove very easily. So under the hypothesis, what is that? F of z has an antiderivative. So say f of z, capital F of z. The capital F of z is nothing but f of z for all z belongs to D. So f is analytic on D. So when f is analytic on D, f dash is also analytic on D according to the previous statement which we have proved. So in the examination you have to prove that result, so that we can understand that f dash is also analytic on D. So if f dash is analytic on D, obviously f of z is also analytic in D. So this is what the moreras theorem says. So with this we have completed all the second unit topic, and we'll start in another video the third unit. I hope that you understood. If any queries is there, you just mail me. I'll just give the answer for the doubts. Any doubts is there? Okay. Thank you.